Hello, we are from Group D. Would like to present our assignment 1. My name is SASHMEETA, daughter of KUMARAGURU, with my ID number EC21072. My team members are DIVYAN, DIVESH, and also Bahirathan. So our assignment 1 is divided into 4 parts. The first part will be methodology, the second part will be design calculation, the third part will be discussion, and the fourth part will be conclusion. I'll be presenting about the methodology. So in Fourier series, we have 4 types of waves. The first wave are square wave, the second wave are sawtooth wave, the third wave is triangle wave, and the fourth wave is semicircle wave. The methodology used for our assignment is Fourier series. So what is Fourier series? Fourier series is a mathematical technique used to represent a periodic signal as a sum of sinusoidal, sine, and cosine functions. It also decomposes a complex signal into simpler sinusoidal components. That is all. Thank you.
Good day, sir. My name is Bahirathan Subramanian, and today I would like to explain about design calculation. This is the waveform we obtained for our assignment 1 with the amplitude of 2 and the period of 2. And then we would like to use exponential Fourier series. This is the general form of it. And then this is the equation we obtained from the waveform above. From the waveform, we figure out that angular equals to pi, and then the amplitude equals to 2, which is x naught. And based on the appendix or Fourier coefficient table, for square wave, we find out the c naught equal to 0, and cn equals to negative j 4 over n pi. And then we also figure out the cn only exists when the harmonics are odd, which is n equals to odds, 1, 3, 5, 7, so on. And cn equals to 0 when the harmonics are even number, which is 2, 4, 6, 8. And by substituting the coefficients we found, we find out the xt formula, which we use to reconstructed the waveform or the graph. In order to sketch both amplitude and phase spectrum for harmonics, we need to do this calculation. For positive harmonics, we can see the modulus Cn equals to 4 over n pi, which is same with negative harmonics. The modulus Cn equals to 4 over n pi, which means there will be no negative amplitudes. And then we did calculation in order to find the phase spectrum for positive harmonics. We find out it is negative 90 degree. And then for negative harmonics, the space is 90 degree. So with this calculation, we list out this table from negative 9 until 9 harmonics in order to sketch the graph. So this is the amplitude spectrum which is sketched, and from this we can see that all the even numbers are 0. Only Cn only exists for odd numbers. And then this is for the space spectrum, just like we found out that for all the negative harmonics, the phase is 90 degree, where every positive number, the phase will be in negative 90 degree. And then same as before, for every even number, the value always will be 0. And that's all from me. Thank you.
Hello and good day. My name is GUNALAN, and today I will talk about the discussion that we made from our assignment. The effect of increasing n to output signal is the series becomes a better approximation of the original signal, and more sinusoidal functions are being added to the sum, allowing for a final representation of the signal shape. And for the Gibbs phenomenon, no matter how many terms we include the Fourier series, there will always be an error in the form of an overshoot near the discontinuity. As the picture below shows, at the top of the amplitude, a ripple is formed as we increase the number of n. Okay, this is the amplitude and phase spectrums comparison. The left one is the calculated, and the right one is we generated from our simulation in MATLAB. As you can see, the phase spectrum in the simulation, the angle is nearing to 90 degrees. That's all from me. Thank you.
Hello, my name is KANNAPATHEY. My ID is EC21070, and I'm from Group D. I'll be explaining the conclusion part of our assignment for signal system. We explore the fascinating world of Fourier series applied to reconstruct the square wave signal. Our focus was understanding the Gibbs phenomenon, which shows up as a rippler near the signal transition during reconstruction of the signal. As we increase the number of harmonics n, these artifacts becomes more apparent, affecting the accuracy near these transitions. Through analyzing the amplitude and phase spectra, we gain insights into the frequency contributions and phase shifts of the harmonics. Increasing n improves the fidelity of the reconstruction, aligning closely with the original signal of the square wave. However, even with higher n values, the Gibbs phenomenon persisted, especially near signal changes. Next, I'll be explaining the coding demonstration using the MATLAB software. First, we need to define the signal parameters starting from the amplitude, period, and also omega. Time vector is referred to the time of the signal, and also the definition of the signal xt, which is a square wave. That will be our original signal. Next will be the number of harmonics. Here I use 10 to simulate the result that will be coming out from simulation. And this is the calculation for the Cn in the positive and also negative values. Okay, so when I click the simulation, first it will show the original and also the reconstructed signal, which overlays on top of the original signal. The original signal is blue and also the reconstructed signal is red in dotted lines. As you can see here, the 10 harmonics is displayed with the Gibbs phenomenon. Next will be the combined phase spectrum of negative and also positive value, where the positive value has approximate to 90 degrees in the phase, and also the negative value. The zero harmonics is labeled in 0 for the phase, followed by the even numbers. Next will be the amplitude. The amplitude has its own value that is similar to the manual calculation for the odd numbers, and for the even numbers, it's maintained as 0, as also for the C naught, that is including the negative, that will be in 0 for the amplitude. Now I'll be showing you the increment of number of harmonics. Okay, now I'll start with 5. So for the 5 harmonics value, the original and reconstructed circuit will be not as similar as the original circuit. The reconstructed circuit will have some Gibbs phenomenon involved in its reconstruction. And next, I'll be showing the increment of the value n. Now, as I increase the value n from 5 to 10, you can see in the reconstructed signal, it's more towards nearing its original signal wave, as the Gibbs phenomenon applies. That this reconstructed signal, after going through the harmonics and also the exponential Fourier series, it will approach to its original signal, that is a square wave. Now I've increased it another 5 to make it n equals to 15. Now, as you can see here, the wave is more discrete and nearing to its original signal of a square wave. So the more the n increases, the more discrete and also nearing to the original circuit occurs. This is what we are discussing in our assignment that relates to the Gibbs phenomenon and also the exponential Fourier series calculation.